So, what exactly is the stack? Well, you come to the right place.
Take a computer's motherboard, for example, which contains the random access memory, which also contains the stack,
Also known as the main stack.
the motherboard also contains another essential component, named the CPU, or Central Processing Unit, which contains two essential registers, EBP and ESP. And these are both used to create stack frames, which can house different values within computer architecture. And just to clarify, EBP stands for Extended Base Pointer, which always points to the bottom of the stack, while ESP is the Extended Stack Pointer, which updates by pointing.
The extended stack pointer is also dynamically updated, meaning that it is constantly pointing to the top of the stack instead of having to update it like EBP. That means that in order for EBP to be pointing to the bottom of the stack, it has to be pushed onto the stack at the beginning in order to solidify its position. So within the CPU, as mentioned before, there's the stack registers, such as ESP and EBP, as well as other general purpose registers, the ALU, which does mathematical operations, as well as the instruction set architecture, which we'll focus on right now.
So now we'll start with three commands that are commonly used to establish a stack frame, which are push EBP, moving ESP into EBP, and subtracting ESP by 0x16, which all came from, you guessed it, the instruction set architecture, which came from inside the CPU. So let's start with the first command, push EBP. So essentially, ESP, because it's constantly pointing to the top of the stack, will be at the lower address, while EBP will be pushed onto the stack, meaning that it is in the first stack frame. Notice how it's not yet pointing to any place on the stack yet. Now let's move on to the next command, moving the value of the EBP pointer into the value of the ESP pointer. So now that we have an actual stack frame established, we can now set EBP to the value of ESP to be further incremented to hold different values that will be used in our function calls. Now let's move on to our next instruction, which actually creates a new set of stack frames that we can use to store values in. So when we subtract ESP by 0x16, we create 4 new stack frames that can be used to store variables in. And I know you may be wondering, why is it growing downward, or why the address is getting smaller and smaller? Well, this is because the stack grows downward. And just to clarify, yes, EBP does stay in the same position it was before, while ESP was incremented downward.
So what instructions can we give to actually move things onto the stack? Well, we'll start out with our first command, the double word pointer.
So now you might be wondering, what exactly is a double word pointer and what does it do? Well, it's simply a pointer to a 32-bit size character that's inside of your function call. An example could be a dereference character pointer as well as an integer. So now we'll simply put the variable or the dword pointer at EBP minus 0x8, which I believe is 2 stack frames below.
So now let's move on to our next instruction, utilizing our other general purpose registers. So for this command, we're moving EAX into the position specified by EBP plus 0x4, meaning that we're simply storing it or pushing it onto the stack in that position. This allows EAX to be used to store things in the future, just in case we want to store more variables in that position as well. So last but not least, let's call a different function that invokes a different part of the stack within the RAM.
And just to clarify, these stacks are not separate. They're merely 2 separate sections within one overall stack, as you can see evidenced by the addresses here. And any of these stack positions can be changed, whether it's due to interrupts, administrative instructions, or return addresses, which I will make another video going into the greater depths of these changes. But until then, thank you guys for watching.